Hey guys, here we are, chapter 17. Now 17 only has two sections, and the first section we're going to break up into a and a B. So anyway, here we go. Section 1A, energy resources and fossil fuels. Honestly, we're going to focus on energy resources today, and 1B is going to focus on the fossil fuels. Your essential question: how are fossil fuels used to generate electricity in a power plant? You need to know how a power plant works, and we'll get into that in more detail in a bit. All right. Energy resources and fossil fuels. Now, a fossil fuel is just a non-renewable energy resource that has been formed from the remains of organisms that lived long ago. Fossils, right? Examples of this are going to be oil, coal, and natural gas. So organic molecules that we can now burn. Most of the energy that we use, turning lights on, electricity, running my camera, the computer, the whole 9 yards, come from this group of natural resources that we just call fossil fuels. We use fossil fuels to run cars, ships, planes, factories, and to produce our electricity. Now, fossil fuels are central to life in modern societies. Back at the beginning of the Industrial Revolution, 1850s, we began relying very heavily on fossil fuels and have ever since. So the supply of fossil fuels, though, is limited. It's a non-renewable resource. It will not come back in a human lifetime. Obtaining them and using them actually has environmental consequences. There's land disruption just to try and get them out of the ground. And then when we burn them, they're releasing carbon dioxide, nitrous oxide, sulfur dioxides, various greenhouse gases, along with other pollutants. And it's just part of the danger of them. We use different fuels for different purposes, right? Now, the four main purposes that we use fuel: transportation, cars, trains, planes; manufacturing, making things; heating and cooling buildings, and we often will use different sources for the two; and then generating electricity, which is going to run machines, appliances, many, many things. And different fuels go into the different ones. By and large, we use oil or petroleum products for vehicles, and we oftentimes use coal to try and produce electricity. It's a little more complicated, but we get the idea. Now, electricity power. This is, on demand, right? I need my lights and I flip the switch and I have electricity. Now, since electricity is more convenient to use, the energy and fuel is often converted before it gets used. For me to have my lights on, well, I need electricity, and it has to be generated. It's easy to use, but somebody out there is generating it, and then I pay for it by how much I use. If I turn on 5 light bulbs, it costs me more money than if I only turn on 3, right? And we kind of pay for it as we go. Now, electricity can be transported very quickly across great distances. So it's generated out there at the plant, but it travels across the power lines very quickly. And this makes it a good source of power for things like computers, light switches, and more. I don't have to go put coal in and fire it up and get it to it's just kind of ready to go on demand, right? I flip the switch and I have my lights. 2 disadvantages of electricity. It's very difficult to store. We can have batteries, but I'm not really storing for my house typically. And other energy sources have to be used to generate. So I have to burn the coal to generate the electricity and get it here. And there's efficiency loss. I go from high quality energy and I'm going to get a lower quality on the second hand because of the laws of thermodynamics. Energy can't be created or destroyed, but it can be transformed. But in that transformation, it goes from a higher quality energy to a lower quality energy because some of it gets lost along the way in the process to waste heat, typically. So, exactly how do we generate electricity? Well, we need an electric generator. And this is simply a device that converts mechanical energy moving around into electrical energy. Generators produce electrical energy by moving an electrically conductive material within a magnetic field. Most commonly, we take a copper coil, a coil of copper, and we spin it around next to a magnet. By moving a electrically conductive material, a copper coil, in a magnetic field near a high-powered magnet, it generates electricity. This is just a physical property and the relationship between magnetism and electricity, in this case copper, which conducts it. Now, most conventional or commercial electric generators convert this movement of what we call a turbine. Something has to spin around. What's spinning around inside of the turbine is a copper coil by a magnet. So we have to get this copper coil spinning. What we do is we get like a loop, and the loop spins around, and every time it goes by, it conducts a bit of electricity. So a turbine is simply a wheel that changes the force of a moving gas or liquid into energy that can do work. Moving gas usually in the form of steam, like you heat it up, the water boils, steam spins my turbine. Or in a dam, falling water, the moving liquid is spinning my turbine. So the turbine spins a generator to produce the electricity. Well, let's take a look at a diagram. I'll stick it up big for a little while and shrink it down. So in the far left-hand side of it, we have our coal. The coal gets lifted and dropped off into the furnace. Now we can burn coal, we can burn natural gas, we can burn oil, we can burn sticks, it doesn't matter. We have to heat water to boiling. So in this case, we're using coal, heating water to boiling. Steam is going up and then spinning our big steam turbine, that thing up on the top. The turbine is spinning, and this in turn spins our generator. So we've just got a big fan, if you will, there, spinning it, causing the generator to spin. The generator is where we're generating the electricity, and that electricity can then be piped off to your house, my house, the school, what have you. Now the water that's spinning, this is very hot water, obviously, steam, and that is captured, cooled down, condensed, and it goes around and around. So all power companies need lots of water because they have to keep this operation cool, otherwise it would heat up. You need water for the steam, and then we have to condense the steam back down into water. But this is, by and large, how a generator works and how we create our electricity. But it has to be created 24/7. We can't store it very effectively. Once again, now sometimes with solar panels, you can hook up a battery to your house, store it for a while, but most of our electricity on a city-wide is just being generated all the time, 24/7. World energy use, how does the world use energy, if you will? Well, everything you do, from the food you eat to the clothes you wear, requires energy. Like when I eat food, I still have to have mechanical energy, right? Even though the food is energy for my body. But everything requires energy. And there are very dramatic differences in the fuel use and efficiency throughout the world. Some things are higher efficiency than others. Now, people in developed countries, more developed countries like North America, Europe, Oceania, by and large, use more energy than people in less developed countries, by and large, South America, Africa, Asia. Now, within developed societies, even, there are differences in energy consumption. If we look at the chart back here, this is showing a per capita. Now, we're showing the difference from 1990 and 2006. I wouldn't really focus on those as much as the per capita. Canada, they use more energy per person than even us in the United States, but we're pretty similar. Canada's colder, right? So it takes a little more energy to heat, et cetera, by and large, than the United States. Switzerland, however, very cold as well, but their per capita energy use is much less. This is good. Go all the way down there to Indonesia. Indonesia, a less developed country, and their energy use is much less as well. So there can be a big difference in the per person amount of energy use. Typically, a more developed society, a more affluent society uses more energy than a less developed. It's expensive, right? Costs money. The more money you have, the more you tend to spend. Now, let's talk about the energy use in the United States. I'll throw a pie graph up here. So this is just showing, as we looked at, the United States uses more energy per person than most other countries. And about 25% of our energy is just used in transportation. We got to get things around, right? Publix truck carrying groceries here, the Best Buy carrying electronics there, you and I getting to school, going to work, whatever it might be. Now, industry, manufacturing, making things is about 38%. Commercial, 16%, residential. Now, industrial here is going to also wind up being agriculture. It's kind of lumped in, it's not separated out in that. But this is, once again, just roughly how the United States is slicing up the pie of our energy use. Now, other countries, such as Japan and Switzerland, really depend very heavily on rail systems because they're a much smaller and more compact country. So you know, more the density, right? More people per square kilometer. They tend to use public transportation much more than we do in the United States. Now, in the United States and Canada, we have some of the lowest gasoline taxes in the world. So there's very little incentive on our part to conserve gasoline when it costs so little. It's like $2.50 for gasoline around. My car's electric, I don't buy it much, so I'm not exactly sure, but in this neighborhood, other countries would be paying the equivalent of $7, $8 a gallon for gas. Our gasoline taxes are incredibly low, so we don't have as much incentive to save money, and we don't take public transportation as often as a lot of other countries, making our overall energy use go up. Also, countries that have limited fossil fuel resources. Not everybody has as much coal, oil, and natural gas just under the ground where they live. They tend to supplement a greater amount of their energy with other energy sources, whether that's hydroelectric, nuclear, now wind and solar are coming in much more of their own, and other countries make much more extensive use of other power sources. Once again, if they have to buy all of their fossil fuels from another country, it's more expensive, and they just rely on different technologies. Because these fossil fuel deposits are not distributed evenly. So how do they form? Where do they come from, if you will? Well, by and large, oil comes from dead plants and animals. A lot of these would even be microscopic animals. But anyway, it's oils from leftover animals. Coal is from leftover plant material. Natural gas is given off from both of these processes, but especially over an oil field, I'll be way down under the ground, but under the oil field, there'll be a bubble of natural gas right above it. But also where we have coal, natural gas is found there. So anywhere we find coal, anywhere we find oil, we also find natural gas. Now we have an abundance of oil in Texas and Alaska, but very little in Maine. Even in the United States, it's not distributed evenly. The eastern United States produces more coal than really any other areas. And the reason for this lies in the geological history of the areas. The Appalachian Mountains, pushing up from here, these tectonic plate movements are the heat and the pressure necessary to create the coal. If you look at the picture up here, the map of the United States, we can look at it. Now, the purple, these are our coal deposits. So along the eastern, the Appalachian Mountain Range, you see coal all up and down there. Midwest, we have large deposits as well, but we can see we have extensive coal deposits. The light green, a little harder to see, this is just oil and natural gas. And then the striped areas, these are offshore oil and natural gas. So we in the United States, we're fairly blessed to have pretty large deposits of all three: coal, oil, natural gas. We don't get as much natural gas off the areas of coal, but as we do coal mine, natural gas does escape and leak out. Natural gas being methane. Now our coal formation. Coal forms from the remains of plants. You know, like we've mentioned, they lived in swamps hundreds of millions of years ago. The ocean levels rose, the ocean levels fell. The swamps were repeatedly covered with sediment. So plants would grow and then sediment would wash over it. The plants would then grow and sediment would wash over it. And these layers of sediment compressed with plant remains, along with heat and pressure, cause the coal to form. So coal is just this mix of plant material along with some other sediments, even little bits of sand. The pressure and heat converted into a rock, but it's a rock that will burn. So much of the coal in the United States formed about 300 to 250 million years ago. Once again, non-renewable energy source, not in a human lifetime. Deposits in the western states formed between about 1 million and 40 million years ago, much sooner, earlier creation. Once again, it all comes down to the tectonic plate and the geological processes. Now, oil and natural gas. Oil and natural gas result from the decay of tiny little marine organisms, by and large, land organisms, but 71% of the world covered in ocean. Majority of our animals have been in the ocean long term. And then they accumulated at the bottom of the ocean millions of years ago, and this seeps down into the little cracks. They get buried in sediments. Same thing, become heated until they become complex, energy-rich carbon molecules, hydrocarbons. This is what is burning. And these molecules over time just sort of migrated, worked their way down into the porous rock formations. And then when they kind of got down into solid bedrock, nowhere else to go, they begin to accumulate. They accumulate there, and under the pressure, this is what forms them. This will wrap it up for the first section. Come back next time for section B, and we'll focus a little more in detail about these specific fossil fuels. Guys, that is it. Take care, and we'll see you next time.